Last time in reading in order, we walked a sentence through an RNN, an LSTM, a GRU, one word at a time, passing a little memory baton from step to step. It worked, but it had a tell. By the time the model reached the end of a long sentence, the beginning had faded. Memory leaks. So here's the question that broke the whole field wide open. What if a word didn't have to wait its turn? What if every word could look at every other word all at once and just decide for itself what's relevant? That's attention. And today we're not going to import it. We're going to build it by hand with nothing but matrix multiplies. We're still firmly in the build stage of our pipeline, but we're going one level deeper than usual. We're building the single operation that the entire transformer is made of. Start with the contrast. An RNN reads like you read a paper through a mail slot. One word slides past, then the next, and you're constantly trying to remember what came 3 words ago. Attention throws the whole page on the table. Every word can see every other word in a single glance. No baton, no waiting, no fading. One shot. Here's the core idea, and it's almost embarrassingly human. Take a little toy sentence. 5 words. The cat sat because it. When the model gets to it, it has a question. Who is it? So it turns to the rest of the sentence and asks, literally, who here is relevant to me? Every word answers. Cat raises its hand the highest. That's attention, each word polling the room about itself. To run that poll, every word plays 3 roles at once. The query, that's what I'm looking for. The key, that's what I advertise about myself to others. And the value, that's the actual content I'll hand over if you pick me. It sends out a query, looking for a noun I could be. Cat holds up a key that matches, and then cat passes along its value, its meaning, to be folded into it. Query, key, value, Q, K, V. How do we measure match? With a dot product, we take its query vector and dot it against every word's key vector. A big dot product means the directions line up, strong match. A small one means they point different ways, weak match. One query against 5 keys gives us 5 raw scores. Do that for every word and you get a full grid. Every word scored against every word. But there's a catch. These vectors might be long, 64, 128 numbers each. Dot products of long vectors get huge, and huge numbers make the next step, the softmax, go off a cliff, where one score eats everything and the gradients die. So we divide every score by the square root of the dimension, the scaled in-scaled dot product attention. It keeps the numbers civilized. Now the softmax, it takes that row of scaled scores and squashes it into a clean probability distribution, all positive, all summing to exactly 1. Think of it as a spotlight with a fixed amount of light to spend. For it, most of the light lands on cat, a thin sliver spills onto sat, and the rest of the sentence sits in the dark. That row is the attention weights. Last step, and it's where the magic actually pays off. We take those weights and use them to blend the values. 71% of cat's value, a sliver of sats, a trace of the others, add them up. The output for it is now a custom mixed vector that contains its context. It literally carries a piece of cat inside it now. Context gathered in one shot. And notice what we never did, we never looped. Every word's output was computed at the same time, in parallel as a couple of big matrix multiplies, exactly what a GPU eats for breakfast. That's the speed unlock that buried the RNN. But one attention pass is just one point of view, one way of asking what's relevant. Next episode, we give the model many eyes on the same sentence and wrap them in the layer that changed everything, the transformer block. Okay, to the code. It's about 50 lines across 3 short pages, and it's shorter than you'd think because attention really is just 4 matrix operations in a trench coat. We'll set up a tiny 5-word toy sentence, build a self-attention layer as a Keras layer subclass, run it once and print the attention matrix so we can read it with our own eyes. Page 1 imports TensorFlow, Keras and NumPy, then our toy data. 5 words, the cat sat because we don't need real embeddings to see attention work, so we fake them. A deterministic random 5x16 matrix, one 16-dimensional vector per word with a fixed seed, shape 1, 5, 16, batch of 1, 5 tokens, 16 features, and because we'll seed the layers weights too in a moment, your matrix will come out identical to mine. Page 2, the layer itself. In build, we create 3 dense layers, WQ, WK, W, each with no bias, each seeded, each mapping our 16 dimensions down to a D model of 8. Those seeds are why this run is reproducible, even though nothing is trained. These 3 little projections are the only learnable weights in attention. They are what turn one input vector into its query, its key, and its value. Still on page 2, the call method, the whole mechanism, 6 lines. Project takes into Q, K, V, compute scores, tf matmuli q k transpose b is true. That's Q times K transpose, every query dotted with every key. Divide by tf.sqrtd to scale. Run tf.nn.softmax along the last axis so each row sums to 1. Then tf.matmul weights v to blend the values. We return both the output and the weights because the weights are the part we want to see. Page 3. We instantiate the layer, call it on our fake embeddings, pull out the 5x5 weight matrix, squeeze off the batch dimension, and print it row by row with the words labeled. So each row reads as this word's attention, spread across the sentence. We round to 2 decimals so it's human readable in the terminal. And there it is. Look at the 8 row 0.71 on cat. Our hand-built attention with seeded but untrained weights and no training at all already routes it toward cat the hardest because that's the geometry of the dot product before a single gradient step. Train those 3 dense layers on real text and these numbers become genuinely meaningful. That's the engine. Next episode we run 8 of these in parallel, stack them with normalization and residual connections, and we'll have built a real transformer block, multi-head attention, norm and residuals. See you there.